All right, welcome to this explainer on the cross product. If you are an engineering student staring down a linear algebra exam, you are in exactly the right place. Today, we're focusing on mastering three-dimensional geometry, specifically areas and normal vectors. This is part 2 of our Mathematics I series, designed specifically to be your ultimate exam prep guide. So here's our roadmap for today. We're going to hit the perpendicular problem, define the cross product, check out the determinant formula, walk through a step-by-step example, and wrap it all up with a quick recap and some real-world engineering connections.
All right, part 1, the perpendicular problem and finding normal vectors.
So let's dive into a classic 3D geometry dilemma. You're practically guaranteed to see this on your next linear algebra exam. Imagine you've got two intersecting vectors in 3D space, right? Together, they basically form a flat plane. Now, the big question is, how do you find a third vector that shoots straight out, perfectly perpendicular to both of those original vectors at the exact same time?
Well, we call this perfectly perpendicular direction the normal vector. This is absolutely crucial for your studies. Anytime you need to analyze a surface, calculate fluxes, or figure out structural loads, you're going to need this. Basically, whenever you have to ask, hey, which way is this 3D surface actually facing, you are looking for its normal vector.
Moving on to section 2, defining the cross product and how we do these calculations in R3. So, how do we actually find this thing? Well, the ultimate mathematical tool for calculating a normal vector in R3 is the cross product. Geometrically, we use what's called the right-hand rule to find the direction. Try this out. If you point your right thumb in the direction of vector x and your index finger towards vector y, your middle finger naturally points in the direction of the normal vector. That is your cross product, x cross y. But here's the really cool part. It doesn't just give us a direction. It gives us a very specific magnitude, too. The length of this new vector is exactly equal to the area of the parallelogram spanned by your two original vectors. So it's basically two incredibly useful pieces of geometric info rolled into one single operation. Section 3, the determinant formula, where we actually calculate the vector. Now, that visual intuition is great for understanding the why, but to totally ace the exam, we need the how. We need to compute this algebraically using vector components. You'll see this really beautiful kind of crisscrossing pattern mapped out here. To get the components of your new normal vector, you literally multiply diagonally. For the first component, you take x2 times y3, and then subtract x3 times y2. Then you just repeat that crossing pattern downwards for the other components. I know, it looks a little messy at first glance. But honestly, once you get the physical motion of this crossing pattern down with your pen, it becomes total second nature.
All right, section 4, a step-by-step worked example to put this into practice.
Let's see how this actually plays out in a real exam scenario. We're going to slow things down a bit and walk through a full step-by-step example straight from the source material. We'll use two vectors. U is 3, -1, 2, and V is -3, 2, -3. To guarantee you get full marks, I highly recommend following these 3 steps every single time. 1, set up the vectors side by side. 2, do the algebraic cross multiplication very carefully. And 3, which is where a lot of students drop points, always verify your work. Let's get into the math. Okay, so by lining up our components side by side, we can carefully apply our cross multiplication formula. Let's walk right through it. For the top component, we look at the middle and bottom rows. -1 times -3 gives us 3. 2 times 2 is 4. 3 minus 4 leaves us with -1. Now, for the middle component, we look at the bottom and top rows. 2 times -3 is -6. 3 times -3 is -9. So -6 minus -9 gives us a +3. And finally, for the bottom component, 3 times 2 is 6. -1 times -3 is 3. 6 minus 3 is 3. If we watch our minus signs closely, which is super important, we see our new normal vector is exactly -1, 3, 3. Now listen up, because here's a massive exam hack. Never, ever just calculate the cross product and instantly move on to the next question. Always check your final answer by taking the dot product against your two original vectors. If both of those dot product calculations equal 0, you know for an absolute fact that your answer is perfectly orthogonal. Let's check side A. 3 times -1 plus -1 times 3 plus 2 times 3. That is -3 minus 3 plus 6, which is exactly 0. Nice. Now side B. -3 times -1 plus 2 times 3 plus -3 times 3.
That's 3 plus 6 minus 9, which is also 0. Boom. We know for sure our vector, -1, 3, 3, is 100% correct.
And hey, remember our geometric definition from earlier? We can now effortlessly find the exact area of the parallelogram formed by vectors u and v. We just need to calculate the length, or the norm, of our resulting vector. That's simply the square root of -1 squared plus 3 squared plus 3 squared. 1 plus 9 gives us the square root of 19. Just like that, from raw coordinates, we've pulled out the precise geometric area. How cool is that? Finally, section 5. Let's do a quick recap and talk about some real-world engineering connections.
Let's really lock these concepts in before your exam. If you only remember 5 things from this explainer, make it these. First, the cross product produces a strictly normal orthogonal vector. Second, it follows the right-hand rule for its orientation. Third, the length of your output vector is literally the geometric area of the parallelogram. Fourth, it's strictly antisymmetric. That means if you flip the order and do y cross x, you get the exact opposite vector, -x cross y. And fifth, your golden exam rule. Always verify your result using the dot product to make sure it equals 0. As you move forward in your engineering career, keep in mind that the cross product is way more than just some tedious algebraic exercise. It is the fundamental tool you are going to rely on to compute fluxes across surfaces, figure out spatial orientations, and really understand complex 3D rotations. So next time you're looking at a sleek curved architectural surface or, say, a really complex rotating turbine, don't just look at the object. Ask yourself, where are the invisible normal vectors and how is the cross product quietly holding our physical world together? Good luck on your exam. You've got this. And keep explaining the world around you.